Hi there. So in this video, I'm going to talk about a very interesting thing that actually came up during the course of a discussion recently. This was regarding a certain project where there's a bunch of SKUs, like large number of SKUs, and there's of course then your marketing channels. So we were trying to understand what is exactly the relationship between ad spend and say sales. Okay, so very simple understanding, and not exactly that, not just between these variables, but generally how much ad spend is actually contributing to sales. So there is obviously the understanding that there's going to be other channels, there's going to be other things that's going to be contributing to overall sales and revenue and contribution margin, so on and so forth. So the suggestion actually came up during this discussion that we can use correlation as a form of association uh, to understand the association between ad spend and sales. So correlation is useful. First of all, I mean, let's not take that away. Correlation has been around for a while, and it's a very fundamental type of statistical analysis. However, there are risks to only be limited to correlation. Correlation can give very misleading results if you don't go further. So that's exactly what this video is going to be about. I'm going to take three different cases. I'm going to start with the simplest form of regression, um, and we're going to see three different cases. The first will be non-linear relationships, and by that I mean the relationship between x and y, and specifically it will be a quadratic relationship. We're going to see that correlation can be misleading there. We're going to also see interaction terms, which is how two independent variables actually combine together to create another third variable. And there's also that case where when when interaction terms rather are present, the correlation can actually be misleading. And the third and the final one we're going to see is that of multicollinearity. So multicollinearity is the case where, quite a mouthful, right? Multicollinearity is where the independent terms are actually correlated among between themselves or amongst themselves if they're more than two, and that can also give rise to a misleading understanding of the actual relationship if you only look at the relationship between the independent variables and the dependent or the target variable, if you only look at correlation. So let's get started. What I'll do is first, give you a rough sketch of what regression, if especially for those who are somewhat uninitiated in the mathematical formulation of it. So this is what regression really looks like. So if we had to just give a second here. So a regression is nothing but you have a dependent variable y, and you have then let me actually just change the color here. Yeah, perfect. So you have a dependent variable y, and then you have suppose your coefficients. So this is the intercept beta 0, and then suppose in the simplest form of equation, this can be an equation, right? So you have y, and then you have your coefficients for the independent variable x, and then you have an intercept. So the examples that we are talking about, and this, by the way, this is a linear regression thing, so this will look something like this, where you have the different points distributed across the line, and this is somewhat a good fit of the distribution of the different points of x. So these are the different x's plotted here. So this is your x, this is your y. Now the examples that I'm talking about, first of all, I'm talking about, suppose, a non-linear relationship. Now this is very important, and we have to understand something here. It's easy to confuse this. Non-linearity can actually be seen in two ways. Non-linearity, first of all, remember how I described it right now, is in the way how x and y are related, right? So this can be, for instance, y equals to beta 0 plus beta 1 x square, right? X square. So y equals to beta 0 plus beta 1 x square. This is basically a quadratic relationship, right? So this is not linear between x and y. So this is a kind of relationship. And if you're going to talk about how this relationship actually works out. So this is basically going to look something like this. All right. So there is a quadratic relationship between y and x in this case. But if you look at, suppose y equals to beta 0 plus, suppose, beta square x. Now the point is that this is a quadratic relationship between x and y, but it's still a linear regression model. This is something that you have to remember. This is important in terms of terminology, but it's very crucial, because the parameters, I mean, which are here, the coefficients, these are still linear. I mean, the highest power is still 1, right? But when the power becomes more than 1, suppose this is beta 2 beta square x, and this can go on to, suppose, beta cube x square, or whatever, it can go on to anything at all, right? It can go on to, like beta n xn or beta n xn minus 1. So this is basically your nonlinear regression model. So we are not talking about this kind of model here. We are talking about this type. In this specific instance, the nonlinear relationship between x and y. Okay, so that's the kind of nonlinearity we are talking about. So just needed to explain that bit. And moving on to the next example, we're going to talk about interaction terms. So by interaction terms, I mean, in the example that I showed, it's beta 0 plus beta 1 x 1, suppose. So suppose this time, instead of one independent variable x, we have x1 and x2. Okay, two independent variables. These are independent variables, right? So these are the variables that are basically, the relationship among them is causing an output. So then you have beta 2 x2, suppose, and this is obviously a regular, just another version of the equation that we saw here, right? This one, but only with one more independent variable. But suppose we have another term, beta 3 x1 x2. So now what we have here is this one. This one is going to be called an interaction term, right? So this becomes your interaction term, because this is basically using a combination of x1 and x2. Okay, and we're going to see how that plays out. In this case also, correlation is going to be misleading if you want to truly understand the relationship between x and y. And then finally comes our case of multicollinearity. Okay, sorry, so this is multicollinearity. So multicollinearity means that your terms here, so for instance, this is we take this part of the equation here. So we say beta 0 plus beta 1 x1 plus beta 2 x2. So your x1 and x2, the correlation between these two is pretty, quite a bit bigger than 0. Okay, so that's your multicollinearity, and this is something that you would generally try to avoid. Okay, in this case also, we'll see that there is actually a problem when you just rely on correlation alone between x and y. So in this case, what I mean is, in each of these cases, actually what I really mean is the correlation between any of these terms, right? So if you take this one, for instance, so correlation x1 and y, this is not going to be a good way to look at the association. Okay, you can't just stop there. At least this can be a starting point, but you can't stop there. So now I'm just going to go back to my document here. So now that the concepts are clear, what I actually mean, so this is that example that I was talking about. See, first of all, we had that linear model. Both are linear regression models, but the association between x and y is first linear, and then it's quadratic in the second one. So this is the quadratic one. As you can see, this is generated using this is using a generated synthetic data set, but the concept is like this. The regression equation is y regress upon 1 plus x, and y is 1 plus x square. So there is a quadratic term there, and what you had is, between x and y, if you look at the output, and you'll see that the correlation was pretty weak, right? And the R squared, which is how you actually measured, which is the which is sort of the extent to which the model can explain variance in the target variable. Okay, meaning that how much of the model, how much of the target variable's variation essentially can be explained by the model. So that is very low. That should be as close to 100% as possible, or 1. So you can see that that was very low, but the correlation is also very low, right? And this is the linear model when we are taking only y1 plus x. But when we are taking 1 plus x squared, we actually see that the R squared is very high, right? It's close to 0.9, which is 90%. And you see that this is what we are talking about. So we saw that the linear model R squared is only 0.001. And if we just come down here, we'll see that so yeah, it's not even statistically significant for the for the coefficient of x1. But we actually, if you look at the OLS regression results for the quadratic one, you'll see that in this case, one of these at least is statistically significant, which is the x2 one. So that of course is which variable is more important. That's a different consideration, but the point is this is a regular standard regression result. We have a very high R squared. Okay, so possibly in order to understand the model better, you will have to reevaluate it, because in this format, of course, one of the the coefficients of one of the variables is statistically not significant, but the x squared is significant, as you can see. Okay, right. So this was the example. In our case, by the way, x1 and x2 means that this is what stands for our x2. Okay, because we have one squared variable, and so we have this quadratic relationship here, as you can see, right? So the quadratic relationship was not being recognized by the linear model, right? This is the linear model that has been fit, as you can see, the straight line going through here, and that simply did not work, obviously, because most of the points were outside this. So there was a non-linear relationship between x and y. Once we took the non-linear relationship into account, we saw that the low correlation simply did not make any sense. It was a very low correlation, because correlation, and I think this is a point that I should have made at the start, is very much a linear concept. It's only in the linear sense that it actually makes sense. Okay, in the linear domain. If it goes into a nonlinear relationship, it does not make sense. That's why we saw that the moment we did a quadratic modeling, and this was not apparent. I mean, of course, this is a very simple example. If you are somewhat familiar with equations and all, you know that this is an equation of a parabola, and there y being proportional to x square, that sort of a quadratic relationship always is going to look like this, but it may not always be apparent. The graph can be more complex, so you'll have to dive deeper to see if there is non-linearity in it. In those cases, just a simple correlation is not going to give you the right direction at all. It can be terribly misleading. Now let's come to the next example. Remember, I spoke of multicollinearity here. So this is the example where we have high correlation between the independent variables. So if I look at this example here, once again, synthetic data set has been generated in order to create that multicollinearity. So there's x1, and another variable is x2, which is x1 plus a small noise, which means that there is high correlation between these variables. And if you actually take that example, we see that if we actually look at the output, let's look at the output here of the regression example. So 3 regression models have actually been fitted here. The first one is simply between x1 and y, the second one is between x2 and y, and the third one is where we have both x1 and x2, and then we have y. And what we're trying to show here is that for between x1 and x2, high correlation is very high between all combinations, x1 x2, x1y, x2y. So x1 and x2 high correlation, that's your multicollinearity, right? High correlation among your independent variables. So you might think that, okay, x1 and y high correlation, x2 and y high correlation, both have so suppose x1 and x2 are your 2 channels, right? So this can be, say, Facebook ads, this can be Google ads. So you're trying to see whether or not there is a good amount of correlation between ad spend of the channels and sales. So you might think, okay, great, that's fantastic. So my channel is doing really well. But when you take multicollinearity into consideration, what you actually see is that one of these variables, the coefficient of that is very small negative value with a non-statistically significant outcome, which means that only one of these variables is actually relevant to the model, or to actually predicting the variation in sales, which is your target variable. It could be anything. So when you have high multicollinearity, it simply means that you don't really require all those variables. In many cases, there are many ways to deal with it, but it means that by requirement, I mean in terms of the modeling sense. But if you actually think of it from the point of view of what is explaining variance, you actually don't need all the variables there, because it means that just having one in place of two is good enough. In this case, for instance, we have two variables, right? And if that depends on the extent of multicollinearity as well. But because multicollinearity is so high, it's almost like you can have only one, and that's why you see that only one variable, the coefficient of one variable, is statistically significant. So by the way, it has to be, the p-value has to be less than 0.05 from statistics. So the last example that we're going to go to is that of interaction terms. So the interaction term is actually going to show us how this these two variables, if they have a combined variable. So the interaction example is where you have x1 and x2 both. So we have four equations in this example. So we have four examples where we have a correlation between x1 and y. Let's come to the output here. So we have a correlation between x1 and y, we have a correlation between x2 and y, we have individually x1 and x2 present, and then we have another one where x1 and x2 both are present. So we actually look at x1 and x2. These are our independent variables, right? And we look at the correlation. You see the correlation is actually pretty low. Okay. And if you look at low correlation values, and then we see that when we actually look at the r squared between x1 and y, x2 and y, these are all very low. Okay. And when we look at main interactions, main effects means that this is the main effects model, as you can see, where we have x1 and x2 both, but individually. But when we have interaction, the r squared is very high. Okay. And if you look at the coefficients also, you'll see that the interaction variable x3 is actually your interaction term. That is very statistically significant, and it has a decent coefficient as well, given the comparatively, relatively speaking, that is statistically significant. The other two are not. Okay, so this is again a great example where the interaction term, when present, is completely changing your perspective. You thought that individually these are not doing as much in terms of explaining variance, because you see that correlation wise, even if you run the individual regression models, the r squared is low. In fact, the r squared is pretty high. This is the multicollinearity example. Yeah, the r squared is actually low. You see, between x1 and y, between x2 and y, the r squared is low. Okay, but when you actually take the interaction term into consideration, you see that the r squared is high, because each of these may have a low correlation value between with the sales variable or the output variable, but together, when you're considering interaction terms, they actually explain a lot of variance. So we saw two cases here. One is the case that you have high correlation, but which is the multicollinearity example, for instance. But we saw that the high correlation does not translate necessarily into better explanation of sales, because like I explained, I mean, I'm not going into again. And the interaction example shows us that even if the individual terms have low correlation with the target variable, they sometimes together can actually have a lot of explanation of the sales. So if you leave out any one of these two, it may not be a very good idea. Okay, so that was the overall explanation. Last but not the least, I'm going to quickly walk through why this is so, and we can actually think of it from the point of view of partial r squared. So what we have calculated here at the end in this part of the code, this is for the same example of multicollinearity, because this is where we have multiple terms, right? And we are going to try to see how each of these actually contribute. So what we are trying to understand is R squared, like I said, is a measure of how much the model is able to explain variance in the target variable. So what we are trying to understand is, since we have two variables which are very strongly correlated to each other, how much do they actually individually contribute to the explanation of that variance? This can be understood through the partial effects analysis, and this is what we call the incremental or partial R squared. Okay, don't confuse this incremental with your regular incrementality test and that sort of thing. So in this example, we see that this is the multicollinearity example, by the way. So we see that the partial or the incremental R squared for x1 and x2 are 0.05 or almost 0.06 for x1, and for x2 it's much lower, right? It's 0.0061. The total model R squared is 0.9817. You see that the incremental R squared is actually not always going to be, they're not going to sum to the total model R squared. And particularly in this case, because one of the variables is already explaining on behalf of the other variable the contribution towards the overall model R squared, if that makes sense, because it's highly correlated, right? Both of these variables. So you have one of these which has a much lower incremental or partial R squared. This is what I was saying, by partial or incremental. So we have another thing which has been commented out here. There's something called Shapley R squared decomposition as well, and that actually, those will total, the sum of those two is actually going to give us the model R squared. But otherwise, we basically have this sort of decomposition of the total R squared, and this is not a linear decomposition. The individual or R squared values may not necessarily always add up to the total model R squared, precisely because they also have correlation amongst them. Now, where does this come from theoretically? So we actually have to look at the definition of R squared itself. So R squared is nothing but the SSR divided by the SSE. So these are basically errors. Okay, so error is basically calculated in this form. Error is calculated in this form, where you have the sum of total sum of total squares or total sum of squares, and then you have the sum of squares of regression, and then you have the sum of square of errors. So error sum of squares, regression sum of squares, and total sum of squares, these are very simple calculations. So SST is simply sum of yi minus y hat square. So this is observed values of y, and this is the mean of those values, right? So it's kind of like standard deviation, only that part of it, apart from the square root and the division by n and all that. But you have then the regression sum of squares, which is basically the predicted values minus the mean of observed values and the square and the sum of that. And this can also be written as SSR is SST minus SSE. Why? Because SSE, which is the error sum of squares, is nothing but the observed minus the predicted. So this is the actual minus the predicted, okay, within the bracket. So these two, this SSE and SSR, actually sum up to the total sum of squares. So your R squared is basically your SSR by SST. In this case, though, you'll see that this is an example where it has broken down the concept of partial R squared. This is where it's coming out to be SSE reduced minus SSE full by SSE reduced. And you'll see that this is what is crucial. You might think that reduced is shouldn't that be like lower than full? Not really, because you have lower number of terms, right? You have lower number of variables rather. So when you have more variables, the model is more robust, and you tend to have more errors, because of omitted variable bias, essentially, in the model. So if you are interested in understanding this calculation, you can let me know, or you can actually go check out the link here as well. Fantastic site. The Penn State University statistics site is great. Like, they have got lots of courses, and most of the material is actually available for free, but you can read it up elsewhere as well. But this is the calculation, which it's a pretty simple algebraic calculation. All it does is really it tells you that, okay, so this is the R squared. If we already have the first variable x1, so if we include now 2 and 3 as well, x2 and x3, then what is going to be the net effect of that? That's why you have on top the SSR, which is the after the inclusion of x2 and x3 in a model which already has x1, and then at the bottom you have SSE of x1. And finally, after some algebraic manipulation, you finally get this version here, SSE reduced minus full by reduced. So this is where it is coming from, this partial R squared, and this I think is at the heart of this understanding as to why when multicollinearity is present, there's usually this sort of difference, or this sort of a complete demarcation has to be drawn between how you see individual correlation between the independent variable and the output variable, and also finally the actual model R squared. So hope this was clear. These are three examples that I showed to that I picked out. There can be some other examples as well, other cases as well, where model R squared may not be, or rather the actual association of the variables with the target variable and their influence on the total contribution to the variance of the target variable may not be fully captured by just looking at correlation alone. I'm going to be talking about such more statistical concepts which are often not fully understood by marketers because they don't deal with statistics as much. I'm going to be probably carrying out a series regularly, at least over the next couple of months. So do keep an eye, do watch out on my channel, do watch out for new content, and thanks for watching. If you have any questions, do let me know in the comments as always, and I'll see you in the next one. Thank you.